The floor is yours.
All right, thank you very much for inviting me to this talk. Sorry that I can be in person. I'm actually just coming back from my wedding. So yeah, but okay, I'm going to talk about structuring skills for manipulation learning. So in the future, we obviously want to have robots that can work in lots of different kinds of environments. We want robots that can help out in hospitals, do household chores, cook healthy meals, lots of different kinds of tasks. And so this idea of a general purpose robot that you can easily adapt to different kinds of application domains is obviously very exciting, but it brings a lot of challenges. And so really one of the big questions we ask in my lab is how do we sort of get robots to that general purpose area? And to do that, we really believe that we need robust and versatile manipulation skills. So these are skills where we can detect errors, we can recover from errors, we can avoid errors ideally for robustness, and we can also generalize between different kinds of objects, different kinds of tasks, reusing information, and that's really where that versatility comes in. So if we want to get these general purpose robots, I think there's kind of three key things I want to talk about today. Which are sort of, I see as sort of key to reaching that goal. One of them is that we want to be able to use suitable representations, especially suitable representations of skills for efficient learning. So often we use very general purpose skills, but I think it's much more efficient if we actually have more specialized skills and if we give that ability to choose the representation to the robot. I think it's also very important that robots can sort of identify what needs to be learned. So when do we need skills? What should these skills be focusing on while they're learning? And again, we want to put that sort of empower the robot to make these choices itself, so that if we have a non-roboticist working with the robot, then we don't need an engineering degree to set up new skills. And finally, I'm going to be talking a little bit about preconditions, which I personally find very important for getting robots into the real world. And the idea there is really that a robot that's going to be general purpose, that needs to work in these very unstructured environments, needs to be able to model and reason about what it's actually capable. So I think we can actually get robots into the world much faster, much sooner, using less impressive skills if the robot is actually capable of determining when or when not it can use different skills. I'm going to start off with the suitable representation. So we want to be able to have suitable representations for efficient learning and manipulation. So when we think about manipulation skills, here we have an example of screwing in a screwdriver. We can often break this down into multiple subtasks. So first of all, just inserting the screwdriver into the screw, and secondly, rotating the screwdriver. But each one of those skills can also be subdivided into separate controllers. So for example, for the one on the left, we have a reaching and alignment. So we need to make sure that the screw and the screwdriver are aligned, but we also need to make sure that the tip goes to the hole. But then when we go to the second one, we still want to have sort of alignment there, but now it's more about force control and sort of pushing into the screw while also rotating around its axis. And so what we see here is that what we really want is controllers that are sort of object-centric and very modular, right? So we can kind of take different kinds of task axis controllers, whether that's reaching, aligning, pushing, or rotating, and compose them together to create an actual skill. And many of these, skills are going to have shared controllers between them. And so what we've been looking at is how we can actually compose different single-axis object-centric controllers in order to create skills, right? And as a guiding example, here we have a green robot, and it has a library of different skills. So it has, for example, some position controllers, it has some force controllers, it has certain anchor points in the environment, which are these controllers are associated with. And the goal is for the robot to slide this object up to the top of the corner. Now, the way that we can sort of combine different controllers is using a hierarchical control. So effectively, we can have the robot learn to not sort of choose individual actions, but choose a prioritized list of different controllers. So in this case, the highest priority is this force controller, which will make sure we keep good contact. And then the second controller is sort of moving up to that corner. But obviously, we don't want to sort of just add both of these together because that's going to apply an excessive force. So instead, we want to be able to project the second controller, or the first controller, I guess you could call it, into the null space of the 0th controller. All right, and now we get a nice action that's going to allow us to push against the surface and actually slide up the object to the corner. And our initial approaches looked at doing this. We learned a neural network for selecting controller every n steps. We created a expanded MDP formulation for sort of selecting one controller after another using the previously selected controllers as part of the state. And we could show that we could learn fairly efficiently in simulation how to perform these tasks. This is still 14 million steps, so this is definitely restricted to simulation at this point. But we can actually learn very robust kinds of policies that sort of naturally switch between these different kinds of controllers and hierarchical controllers as we sort of reach different key points. What we've been looking at more recently is actually how we can sort of go beyond just selecting different controllers, but actually sort of composing them even more in more detail, and also learning some of their low-level parameters. So rather than just sort of saying we've been given these controls to choose from, we actually sort of populate the environment with a whole bunch of sort of key points on the objects, key points on the end effector. We have different task axes that could be associated with each one of these object key points. So it could be a surface normal, it could be gravity direction, it could be an object axes, it could be world axes, lots of different sort of axes that you can consider about. And we also have different controller types. So we have, for example, we still have force control, we have linear trajectories, we have DMPs if we need a little bit more shape. We have neural networks if we need something really general. We also have alignment controllers for orientation. And the idea is that we can sort of create this massive range of different kinds of skills by simply combining multiple ones of these. And then not just selecting the skills, but also learning some of the parameters. So for the DMPs, for example, we need some weight parameters. And if we want to sort of stack an object on top of another object, we may have something that says, let's use a linear controller for the radial direction and a DMP for the up and down. And for the radial, there's not a lot of parameters to learn. For the DMP, we have maybe 5 parameters for the DMP. And we want to be able to sort of extract that structure and also learn the parameters. Now, doing that completely from reinforcement learning is going to be very inefficient. It's going to take a lot of time. And what we really want to do is we want to have scalable robots. We think that it's important that a lot of skills can be learned directly on the real robot. We don't want to rely on very accurate simulations. And so what we do is we give the robot just a handful of demonstrations. So under 5 demonstrations. And we have the robot use that to quickly eliminate large numbers of sort of ill-fitting demonstrations or skill representations, right? So if you have something that says, oh, well, it's just a straight line, but the demonstration is obviously an arching motion, you can quickly remove that. We can also incorporate some heuristics or priors. So for example, if we move towards in close proximity to a point, then that's likely to be a key point on the object. Doesn't necessarily have to be, but it is a possibility. It's more likely than something that's 3 feet away. And what this does is it's going to sort of remove lots of different sort of points in the space of different task axis controllers. It's not going to reduce it down to 1. There's obviously still going to be a lot of ambiguity. If you're swiping down a surface with the normal pointing upwards, then whether it's the normal or gravity, it's impossible to know from demonstrations, but we can effectively reduce a large space of these different controllers so that we have a more structured space in which to explore using reinforcement learning. And then the final reinforcement learning is really just about resolving some of those ambiguities and refining the parameters from the initial demonstrations. And here you can see some examples of this. So we have a box opening task and a surface wiping task. And down here you can see the learning curves. I think it was about 4 trajectory steps per full attempt. So the robot can also choose to sort of reattempt something if it fails once. And you can see within a reasonable amount of steps, we can actually learn these different kinds of behaviors quite robustly on the real system. And so this is why I think it's very important that we have the robot actually choosing a suitable representation of its skills rather than always forcing it to go for the most general kind of representation. The second thing I want to talk about is having the robot actually identify what needs to be learned. So we often sort of think about robot learning. We set up a task and we want the robot to learn a certain task. And in some cases, the task that we give it, you could actually do without learning or not having learning for the entire part. In many cases, a robot can do quite a lot using a simple planner, right? A simple motion planner, as long as it has an accurate model of the environment, and it can evaluate that at a fairly fast speed, it can actually do quite a lot with that. So a lot of pick and place tasks you could probably do using just a planner. The problem is obviously when our models fail, right? If our planner is working on a model and it's making predictions that are not actually accurate for the real world, then those plans are kind of doomed to fail. And that's kind of the situation where we do need some learning. We could try to learn a model in those situations, or what we did in this case was we actually learned a skill in order to sort of patch the model. So if you have sort of your state action space, you have a region here in green where the model fails, then what you need to do is really learn a skill that has its preconditions at the edge between the green and the blue that'll then bring you to this goal state. And so what we need to do is we need to learn both the skills, but we also need to learn about the situations where the model is valid or where it's not. So in that case, if we have that model validity, we can create a plan, see if it's going to make an error. If we expect that the initial plan is not going to work, then we can sort of plan to the preconditions and have the robot sort of learn that skill to get to the end. And so we explored this in the context of sort of the shape insertion task. And you can see some of the results here on the right. So success means it's a proper insertion. Partial success means we hit the hole, but we didn't get fully in. And failure means that we didn't even reach the hole. And what we can see is that sorry, one second. We have down here our demonstrations of the skill. Again, it's the smaller numbers. We get success rates. They're fairly high, fairly early. And the reason we can do this is because it's a very niche skill, right? It's looking at a very small part of the problem because the planner can take care of most of it. It's really just this sort of threading the eye of the needle part where it's doing the insertion, where we need to learn a skill. So avoiding the obstacle, that can be done by planner. Getting close to the hole, that can be done by planner. It's just the sort of that last sliding into the slot where we need a little bit of extra help, right? And because we've sort of reduced the scope so much for the skill that needs to be learned, we can learn it very efficiently using very small amounts of data. I also wanted to give this example here. So we kind of, in the previous project, I showed that we were learning how to open up a door. In this case, we had one of our students design a model for the door and have a planner plan a motion for opening the door. And it turns out that we can actually open this door without actually having to do learning. So I guess this is kind of a partial dirty laundry slide. But it is kind of nice seeing a robot that kind of says, well, actually, in this case, I don't need to learn a skill. I can do this on my own, even if we sort of change the geometry of the door a little bit. So another way that we can sort of think about determining what needs to be learned is identifying what is relevant and what is irrelevant in different scenes. As we have robots working in very complicated environments in the future, there's going to be lots of objects, and many of them are going to be completely irrelevant. And so what we want to do is we want to take sort of some context variables C, which might be all of the objects in the environment. We want to map them to some skill parameters theta, but rather than taking all of those C variables, we want to reduce it to a smaller set, which we're going to be doing using sort of causal reasoning. So the idea is that I like to think of it in terms of basketball. So you can imagine there's a hoop, there's a backboard, you have the ball, there's some bleachers around, there's maybe a fence if you're outside, maybe some trees, a playground. And if you kind of imagine what you could do with that ball, you can imagine that you can hit against the backboard and that'll go in. You can imagine going against the fence, that's not going to help at all. there's lots of different sort of variations you can imagine. And you can use that sort of internal intuitive physics to reason about which parts of the environment are actually important and which ones are not, right? And obviously, as a human, we know that if I stand for 10 years with the ball just in my hand looking at the basket, I'm never going to get to that level of professional basketball because my internal model is just not that good. I need to actually play to sort of learn it. But I can reduce a lot of the complexity of the scene by sort of imagining which parts are really going to be important or not, and then focus on things like, where's the backboard, and how to sort of use that backboard in order to get a successful hoop score. And so we do this also using the sort of internal simulation. So we assume the robot has a simple model of the world, like a simulation. Usually you would learn the initial weights and then transfer that to the target domain for fine tuning. But we do some additional sort of causal reasoning using that internal model. So what we do is we provide the robot with randomly generated scenes. We then have the robot actually learn to solve that specific task. So it doesn't have to sort of think about the generalization, just specific scenarios, which you can do fairly easily using either reinforcement learning or even a planner in some cases. And once we have that solution, we can start applying interventions. So for example, here we have a block stacking task. If we try to move the orange block, then this task is still going to succeed. But if we change the height of the blue block, then it's going to sort of fail at that point. And that kind of gives us indication that the height of this blue block is very relevant, whereas the position of the orange block is irrelevant. And so by doing this for all the different parameters, we can quickly narrow down the set of context variables that are actually relevant, and then learn the skill for performing the placing using that. And our simulation experiment showed that this makes it a lot more robust also to sort of unexpected domain shifts. So if the colors of the objects change, or if they're a different part of the table, then that can actually improve performance and make it more robust. And we also tried this on a real robot. And even for something as simple as stacking two blocks on each other, we do see that sort of having this sort of narrower scope of states that we're sort of focusing on can make it a lot more robust. All right, and so we have the successful placement on the right and unsuccessful on the left. The last thing I want to mention is this idea of learning the scope of the robot's capabilities. So I'm very excited about the idea of preconditions and sort of taking them beyond the way that we usually use them just for planning. So as a refresher, preconditions are effectively the set of states where when you execute a skill policy, you're going to get the desired effect, right? So if you're trying to open up a door, for example, the preconditions would say that you need to be in front of the door and the door probably needs to be unlocked so that your door opening skill is actually going to succeed. And I think that the preconditions are very important because they allow the robots to identify the scope, right? So if there is something blocking the door, maybe there's a dog sleeping in front of it, or you've got some bags in front of it, and the robot has never been trained for this, that's okay, right? It just needs to be able to identify that it can handle these situations, rather than sort of saying, well, it needs to be able to handle any possible situation in the real world. So the way that I see preconditions is kind of being that that barrier that sort of has to handle the complexity of the real world so that we can have robots whose policy doesn't have to handle every single situation, right? So if there's irrelevant objects such as those obstacles, or objects are being moved or added between scene, if you're trying to cut a vegetable and you don't have a knife, all of these complexities need to be handled by the preconditions. And so we've been doing some work on preconditioned learning. So this is looking at graph neural networks. And in order to make it sort of more efficient for learning, we looked at sort of breaking it down into pairwise relationships. And we actually learned these sort of simpler relationships using embedding approach, so self-supervised in simulation. Again, this is a fairly simple simulation, but these individual pairings are fairly simple. And then the final precondition prediction about whether or not a skill is going to succeed, we leave to the actual real world data, but then we only need like 25 samples. So here we have a scene. The robot's going to sort of see it from different locations or different positions. We get a voxel representation of each of the objects. We have these embedding networks that allow us to get the pairwise relationships between objects, and then the precondition networks that predicts whether it's going to succeed or not. And in this case, it predicts that it's not going to succeed, and in fact, it does start cutting into some other object, which it shouldn't. If we remove that object, though, then it predicts that it is going to work, and so at that point, it is actually a safe cutting motion. Another area that we've been looking into is taking this idea of preconditions and expanding it beyond just skills. So here we looked at actually the preconditions of different transition models and being able to sort of combine them together into one sort of mosaic or collage of different models, with some of them being faster than others, some being more accurate in certain situations. And so what we want to do is we always want to sort of bias our planner to expand the faster models first, while making sure that we're always within the valid preconditions. So we're always going to have valid predictions or accurate predictions given our model. And so with this, we can actually get plans that are both faster, because if we're in free space, we're going to not rely on a complicated physics, only when we get sort of close to objects. And we're also still robust, because we make sure that we only use models that are accurate at different times. Quickly, just wrapping up, I know I'm almost at the end of my time. I want to say that for the pseudo representations, it was very interesting sort of thinking about like different kinds of tasks to look at. We're trying to sort of identify ones that are more challenging for sort of the common priors about proximity and stuff like that. For identifying what needs to be learned, in that case, we definitely did disentangled state right now. There's also certain challenges in terms of, if your simulation doesn't capture all the variables that are present in the real world, how do you handle that? And for the scope of the robot's capabilities, whenever you do preconditioned learning in the lab, there's always a human that had to set up the environment. So there's this sort of innate tendency to have some of the preconditions already be solved for you, which is something that we really, we need to push out into the real world more. I want to thank all of my students in my lab. I've highlighted 3 here, Jackie, Shivam, and Samya. They're at RSS, so if you bump into them, talk to them, say hi to them. But I do want to thank all of my students for all their excellent work. And yeah, just to summarize, I think it's important for scaling robot learning that we use pseudo representations and that the robot chooses these itself if possible. So not general purpose, but more specialized representations. It needs to identify what it needs for the task, so it needs to structure the learning problems as much as possible on its own. And ultimately, no matter how good the skill is, I think it's important that the robot learns the preconditions so it knows when it can and cannot use it. And I think that's going to be a very important step to getting robots into the real world. Thank you.
Oh, thanks a lot for a very interesting talk, Oliver.